I'm determined to tell you something about the convolution rule. I just get close to it, but I haven't quite got there. And actually, I'd like to say something also about why convolution is so important. I mentioned here a paper about images in deep learning it has 3 authors, and these are 2 of them. Maybe you recognize Hinton's name. He's originally English. He was in San Diego for quite a few years, and now he's in Canada. So Toronto and Montreal are big centers now for deep learning. And he's really one of the leaders, and so is Sutskever. So maybe you know that the sort of progress of deep learning can often be measured in these competitions that are held like about every year for how well does some people design and execute a whole neural net. And this was a competition about images. So that is really demanding because, as I said last time, an image has so many samples, so many pixels, that the computational problem is enormous. And that's when you would go to convolutional neural nets, CNN, because a convolutional net takes fewer weights. Because the same weight is appearing along diagonals, it doesn't need a full matrix of weights, just one top row of weights. Anyway, so this is one of the historical papers in the history of deep learning. I'll just read a couple of sentences. So this is the abstract. We trained a large, deep convolutional neural network. I'll just say that it ran for 5 days on 2 GPUs. So it was an enormous problem, as we'll see. So we trained a large deep network, CNN, to classify 1.2 million high-res images in ImageNet. So ImageNet is a source of millions of images. And on the test data, the last sentence is maybe a key. We entered a variant of this model in the competition, 2012 competition, and we achieved a winning top 5 test error rate of 15% compared to 26% for the second place team. So 15% error they got, 26% was the best that the rest of the world did. And so that and when he shows the network, you realize what's gone into it. It has convolution layers, and it has some normal layers, and it has max pooling layers to cut the dimension down a little bit, and half the samples go on one GPU and half another, and at certain points layers interconnect between the 2 GPUs. And so to reduce overfitting, you remember that's the key problem, is to reduce overfitting in the fully connected layers. Those are the ordinary layers with full weight matrices. We employed a recently developed regularization called dropout. So dropout is a tool which, if you're in this world, I think Hinton proposed it again by seeing that it worked. It's just a careful dropout of some of the data. It reduces the amount of data, and it doesn't harm the problem. So the neural network has 60 million parameters. 60 million. With 650,000 neurons, 5 convolutional layers, and 3 fully connected layers. I just mentioned this, and you could, if you just Google these 2 names, you would on the web, this paper would come up. But we're talking about the real thing here. Convolution is something everybody wants to understand. And I'd like to, since I've started several days ago, and I'd like to remember what convolution means. So if I convolve two vectors, and I look for the kth component of the answer, the formula is I add up all the C's times D's, where the index I plus j adds to k. Why do you do such a thing? Because C might be represented by a polynomial, say x plus cn x to the nth. And D might be represented by another one, d1x plus dm x to the m, let's say. And convolution arises when I multiply those polynomials, because for a typical, and then collect terms, because a typical power of x, say x to the k, the coefficients are, well, how do we get x to the k in multiplying these? I multiply c naught times a dk. Somewhere in here would be a dk x to the k. So a c naught times a dk would give me an x to the k term. And a c1 times, everybody sees this coming now? C1 has an x in it already. So over there we would look at dk minus 1 with one less x. So it would be c1 dk minus 1. This is just what you do when you multiply polynomials. And the point is that the way we recognize those terms is that the exponents, 0 and k, the exponents 1 and k minus 1, always add to k. So that's where this formula comes from. We take a c times a d, hiding behind are a c x to the I and a dj x to the j. And when I plus j is k, this is x to the k, and that's the term we're capturing. So this is the coefficient of that term. And let me write it in a slightly different way, where you actually see even more clearly convolution operating. So j is k minus I, right? So it's the sum of ci d j, but the j has to be k minus I. So this is the way to remember the formula for the coefficients in C star D in the convolution. You look at C's times D's. It's a form of multiplication. It comes from ordinary multiplication of polynomials. And when you collect terms, you're collecting C, the IC and the K minus I D, and you're taking all possible I's. So it's the sum over all possible I's there to give you the kth answer. Well, just to see if you got the idea, what would be the convolution of two functions? Suppose I have a function, f of x, and I want to convolve that with a function g of x. Okay. And notice that I have not circled this symbol. So I'm not doing periodic convolution. I'm just doing straightforward convolution. So what are we going to have in the case of two functions? What would that mean, a convolution of functions? I'm in parallel here with a convolution of two vectors. So think of these now have become functions. The kth component has become, really, I should say, f star g at x. That's really the parallel to this.